Okay. So next we are going to write energy balance. So what are all the different terms involved in energy balance, different processes? Conduction. So instead of shear stress, it's conduction. Okay. What else? Will there be a pressure gradient? No, of course not. Okay. What else? Viscous dissipation. So you will have viscous dissipation. Okay. What else? Do we have convection? Yes or no? Do we have convective mode of heat transport? Of course yes. Of course yes. Okay. What else? Excuse me? Work done by? Okay. So we can call it generation term. Okay. So if it's a positive sign if it is generation, it's a negative sign if it is a sink term. Okay. So these are the four processes. So we can easily write down these balances: rho Cp, U, dou T by dou X, viscous dissipation, right? What shaft? Yeah. That's what convection accounts for. That's what convection is already taken into account, right? Dou T by dou Y, so that's your convection term, and that should be equal to the conduction del square T. Laplacian is the mathematical representation for conduction, plus the viscous dissipation. I put capital phi as the viscous dissipation term, plus the heat generation per unit volume. Okay. Viscous dissipation is given by mu dou U by dou Y, dou V by dou X, square of that, plus 2 times dou U by dou X plus dou V by dou Y, the whole square. So that's viscous dissipation. Okay. So this sort of completes the energy balance. Again you can get the same thing from Navier-Stokes. So all that we have done, you can use shell balances and reach the same expression. You can write the Navier-Stokes and reduce the Navier-Stokes, you will get the same expression, and you can also start by describing different processes. So it's all equivalent if you do it properly. That's very important, if you do it properly. Okay. So similarly we can write mass balance. Okay. So what's the equivalent convective term for mass balance? U into dCA by dx plus V into dCA by dy. Okay. So if A is the species and we are monitoring the concentration of the species, so that's the convective term, and that should be equal to the diffusivity multiplied by del square Ca. So that's the mass diffusion. There is no viscous dissipation, so all that we can have is a generation term. If I put N dot as the mass generation term, it could be by chemical reaction, etc., etc. Okay, there could be many different ways, but let's say Na dot is the volumetric mass generation term. So these are the four balances, and of course you can write continuity equation. That is dou U by dou X plus dou V by dou Y, that's equal to 0. So the continuity, moment you say it's an incompressible fluid, the continuity equation is naturally satisfied, right? So we really don't have to solve for continuity equation because the fluid is incompressible and it's a steady state system. We are looking at steady state incompressible fluid. So the continuity equation will always be satisfied. So you don't have to worry about solving the continuity equation. Okay. So all we will have to worry about is solving these 4 equations. Is this linear? Are these sets of equations? Is it linear? Why is it non-linear? Yeah? Convective term and viscous dissipation. Okay. In all the equations or only some of them? Some of them. So which one is linear, which one is non-linear? Yeah? All are non-linear. Mass balance is linear. What makes you think that it is linear? So what's the definition of non-linearity? When do you call an equation linear? Okay, that's one. Fine. And then what else? What else? So note that u and v are so all these equations have to be solved simultaneously, right? Okay. The only difference is that in principle yes it does, except that we have not written the constitutive equation. Okay. So supposing, so it depends upon the concentration level for the species that you have. Okay. Supposing I have a species whose concentration is, let's say, Ca1. Okay. Okay. Now I suddenly have from the solid or from the interface between the solid and fluid, let's say that the species now has transported and it has become 4 times Ca1. Okay. So now the density has changed, right? Density of the fluid has changed. Correct. So moment you, so the first thing is that if you assume that the transport, the velocity effects because of the concentration change is negligible, right? So you can still have incompressible. If you have concentration, if you have 4 times the species that is added, you can still have by actually tweaking with the velocity. You can have a higher velocity flow, you can have gradients, you can play with the gradients du by dx and du by dy and still maintain incompressible fluid. Okay. So incompressible does not mean necessarily that the concentration does not affect the velocity. So in principle, the mass transport it can alter or can affect the momentum transport. Okay. Okay. In fact, you may recall in your transport course, the flux of mass transport was actually, it's called as J. It's defined as the diffusive flux plus the contribution from the convective flux, right? So anytime you have mass transport, in principle it can actually affect the convection of that species in that direction. Correct. Right. But this one tells you that momentum transport affects the mass balance, mass transport here. So they are of course coupled. So for the course purposes, we are going to assume that this coupling is negligible. Okay, we are going to assume that the mass transport does not affect the momentum transport. Okay, this is an assumption that we are going to make, and in fact some of these assumptions would be relaxed in the advanced course. We will not do that here. Okay, so therefore this equation, if Na dot is a linear term. If it is linear, then the mass transport equation will become linear. Okay. Alright. So, to further simplify, we are going to assume that Q dot is 0, we are going to assume that there is no heat generation term, and then we are going to assume that the body forces are 0 to start with. We will actually include body forces when we talk about natural convection, but let us assume for now that it is 0. In order to understand the simultaneous heat, mass and momentum transport, we will make these approximations, and then we will assume that Na dot is also 0. Okay. We will also assume that the fluid that we are actually dealing with is a low viscous fluid, and therefore the viscous dissipation is also not significant. Okay. So, with that assumption, these two guys will go away, these two guys will go away, and this guy will go away. Okay. So, now which are linear here? Which equations are linear? Mass balance is linear. Okay. What about energy balance? That's also linear. What about U? So, if we know U and V, then we should be able to find T and Ca. In principle it is not linear. Okay. So, U and V, if we assume that the viscous dissipation is 0, then U and V are completely independent of the temperature, right. So, if we assume viscous dissipation is negligible, then U and V are independent of temperature, and therefore these two equations are linear with respect to temperature and concentration. So, the real task is to find what is U and what is V. If we know that, we know exact solutions of this. Okay. So, the next what we are going to do is, so the typical thickness of boundary layer is about order of microns. Okay. So, that is the typical thickness of the boundary layer, okay, momentum, heat and mass transport boundary layer. So, because the thickness of the boundary layer is much smaller than the length of the plate or the system that you are looking at, so we can introduce something called boundary layer approximation. Okay. So, yeah, that is the typical order of magnitude, right. It is very small, but still the order of magnitude is very small, right. So, the boundary layer approximation, okay, so supposing if we know that there is so much disparity in the length scale of the boundary layer compared to the actual length of the system that you are looking at, one could make certain approximations. So, note that these are approximations, and we make this so that we can actually get some insight as to what is happening in this problem. Okay. One could actually go and solve all this numerically. No one stops anyone from doing that. One could actually solve them all numerically, but you do not get any major insight by simply going and brute force solving them. Okay. So, we can introduce boundary layer approximations, and the first approximation is that the x component velocity is much larger than the y component velocity. Now, why is this justified? Why is this a reasonable approximation? So, let us draw the boundary layer. Supposing we take a flat plate, okay, what is the x component velocity above the boundary layer? It will be the free stream velocity. So, supposing I call this u infinity, okay. What about y component velocity? Y component velocity, it will be It will be 0 because most of the fluid is actually moving in the x direction. So the V infinity is actually 0 here. So the y component velocity is really present only inside the boundary layer. So the thickness is very small, while the x component velocity is present in x direction, and this length scale is much larger, and also it is the flow is because of the pressure gradient, right, because there is an external pump which is actually forcing the fluid to flow past the object. So therefore the x component velocity is much larger than the y component velocity. So note that there is no pumping in the y direction, it is only the x direction flow. What about du by dy? What can we say about the gradients? Okay. So what can we say about the gradients in boundary layer? Let us say du by dy, du by dx, dv by dy dx, and dv by dy. What about order of magnitude of these four? V itself is very small, right? So these two gradients are expected to be very, very small. Okay. What about du by dx compared to du by dy? Which one is larger? Du by dy is larger. Why is it larger? Why is it larger? Yeah. So the friction is actually present in the at the interface between the solid and the fluid, right? So therefore this friction is now going to introduce gradients, strong gradients in the y direction, right? So the x component velocity, the fluid particles which is actually moving in the x direction, they are now retarded strongly because of the friction that is offered by this surface, and therefore you would expect that there will be steep gradients. Therefore because of that retardation, the gradients in the y direction of the x component velocity is going to be much larger than the gradients that is offered in the x direction itself. And the reason why that is the case is that the retardation that might occur in the x direction of the x component velocity is only because of the shear of the fluid itself. It is not facing the friction of the wall, which is much larger than the shear that is offered by the fluid to its own particles, and therefore you would expect that the y gradient of the x component velocity, that is du by dy, is significantly larger than all the other gradients. Okay, and in fact dv by dx actually is larger than dv by dy. Yes. Yeah. Correct. Then du by dx is 0. So still du by dy is larger. Yeah. But that is only in the fully developed. This is true even inside the boundary layer, even before the fully developed regime. So you are talking about what is the gradient after the fully developed regime, where du by dx is 0. So there it is very, very clear that du by dy is going to be greater because the gradients in the y direction is not 0, we know that. Okay. But even inside the boundary layer, du by dy, that is the y gradient of the x component velocity, is always much larger than the x gradient of the x component velocity and all other gradients because of the wall shear. So that offers a significantly higher friction and than the shear that would be offered by the fluid to its own particles, and that is why this gradient is always larger. Exactly. See, the fluid is moving here. Now because it has seen a wall here, the fluid particles have come to rest at the interface. So now you need to have a definite dv by dy, otherwise the continuity equation will not be satisfied. So that forces a certain gradient in the x direction, and that is going to be much smaller than the y component gradient, I mean y gradient of the x component velocity. Okay, any other questions? Alright, so if we impose these boundary layer approximations, okay, so we can rewrite the model equation. Yes, yeah, sure. So supposing you take, so the wall is present here, right? So you have an interface. Now when the fluid is moving in the x direction, so the pressure gradient is primarily in the x direction, right? Because that's where that's the direction in which the fluid is being pumped. Now as soon as the fluid sees the flat plate, it is exposed to the friction which is offered by this surface. So therefore it's going to retard the fluid particles above it in the y direction, right? But then because some of the fluid particle velocity has now changed and some of them have actually come to 0, right? The x component velocity has come to 0. The continuity equation will force that there has to be a dV by dy, otherwise the continuity equation is not satisfied, and because it's an incompressible fluid, you must have y component velocity in order to satisfy the continuity equation. Now the slowing down or the gradients in the x direction that you will get is simply because of the shear of the fluid offered on itself. So it does not feel the presence of the plate. The gradient that you see in the x direction is not necessarily because of the friction that is offered by the plate, but the y gradient of the x component velocity is primarily because of the friction that is offered, which is significantly higher, and that's why this velocity gradient is larger than all of these. And about these two, it's because the boundary layer thickness itself is very small, so the y component velocity itself is going to be significantly smaller. So it has to go from some 0 at the boundary. So note that the v is 0 here, both x and y component velocity is 0, and if I actually go along this line, let's say this is x1, okay, if I go along this line, you see that the y component velocity at the edge of the boundary layer is also 0, because it's primarily the free stream fluid which is flowing outside the boundary layer, okay. So the gradient is, the velocity is 0 here and it is 0 here, okay. So therefore the gradients cannot be significantly larger. If the gradients are significantly larger, then within small distance it cannot go to 0. So therefore the y component velocity is bounded with value 0 from the surface of the flat plate to the edge of the boundary layer. That is because of, yeah, that's the mathematical way of looking at it. So the gradients are not significantly higher. That's why these three gradients are actually much smaller than the y gradient of the x component velocity. We'll include these boundary layer approximations in the model equation, and we will start looking at some similarity. In fact, you can already see that these equations are similar, okay. If you know the pressure gradient, okay, so that's a measurable quantity, right. So if I am pumping a fluid, I should be able to measure the pressure gradient at which I am pumping the fluid. So if I know the pressure gradient, so that's a constant, okay. Then if you stare at these three equations, they are actually looking very similar. So if this pressure gradient is a constant, then all you have here is u du by dx plus v dv by du by dy, and that's very similar to the terms that you see here. So it's convection equating to a diffusion term, and that's what you see in momentum transport, that's what you see in energy transport, and that's what you see in mass transport also. So you can already see that there is some similarity in the model equations that describes the velocity profile, temperature profile and concentration profile. So we are going to capitalize on this similarity, and we are going to show in the next lecture as to how to actually calculate some of these important properties simply by capitalizing on the similarity of these three equations without solving them, okay. We are not going to solve these equations the way they look, but we are going to try to extract as much information and insight simply by looking at the structure of the equation.